Hello, my name is Jaime Maldonado. I am a PhD student at the Cognitive Neuroinformatics group at the University of Bremen. Together with my co-author Christoph Zetzsche, we investigated the differences between reach-to-grasp and reach-to-place movements executed in virtual reality during the manipulation of different household objects. In physical environments, the sensorimotor features of transport and place movements depend on the characteristics of the manipulated object. Object characteristics like size and weight influence the movement kinematics. Furthermore, different objects produce characteristic sensory feedback in the visual, haptic, and acoustic modalities. Previous research has shown that the kinematics of reach-to-grasp movements are influenced by the object's intrinsic and extrinsic properties. Intrinsic properties are the object size, weight, and type. Extrinsic properties are the distance and the placement of the object with respect to the subject. These properties have been shown to influence the peak speed and the percentage of time to peak speed of the reach movement. Object manipulation in virtual and physical environments differ on the sensory information perceived by the subject. In VR, without haptic or acoustic rendering, only visual feedback is produced during the manipulation of an object. For example, a contact event between the hand and an object, or between an object and a surface, is perceived only in the visual modality. Thus, under these sensory conditions, motor control during object manipulation depends on vision and proprioception. In contrast to physical environments, the lack of acoustic and haptic rendering has two implications. The movement to reach for an object and the movement to place a grasp object are executed under the same physical conditions. For both movements, the subjects either move their hands free in the space or hold controllers for interaction. Furthermore, the manipulation of virtual objects produces a similar motor feedback, regardless of the object types or its dimensions, whereby the subject perceives the movement of the hand and the dynamics of the handheld controller. Considering these factors, the motor feedback is completely equivalent for a reach-to-grasp and a reach-to-place action, and it does not depend on the object. Given that reach and place movements in VR are executed under the same physical conditions, it could be hypothesized that there are no differences between reach-to-grasp and reach-to-place movements. Therefore, if a subject would act optimally with respect to the VR situation, it would use a one and the same velocity profile for the reach-to-grasp and for the reach-to-place action, invariably for all objects. On the contrary, significant differences would provide evidence that the persons adjust motor output as a function of the manipulated object and the task. In this paper, we investigated the differences in the kinematic parameters of reach-to-grasp and reach-to-place movements executed in VR and determined whether these differences depend on the manipulated object. For this purpose, we analyzed the manipulations contained in the HAF dataset. Subjects were given the simple instruction to set the table, for which they took objects out of a cupboard and placed them on the table at will. We chose this dataset due to the large variability with respect to the objects used, the spatial configuration of the objects on the table, the number of objects used, and the order in which objects were manipulated. We analyzed reach-to-grasp and reach-to-place actions with different objects performed by 82 participants. In total, we analyzed 837 reach-to-grasp and 837 reach-to-place actions performed with cups, cutlery, glasses, plates, and wine glasses. We only considered right-hand manipulations for the analysis. We identified the reach-to-grasp and the reach-to-place actions within the hand trajectories available in the dataset. Kinematic features were computed to compare the characteristics of both movements. The peak speed, PS, provides an indirect measure of the speed accuracy trade-off associated with the movement, where lower speeds indicates a more accurate and careful behavior. Additionally, We measure the symmetry of the speed profile by computing the proportion of time to peak speed, PTPS. PTPS values below 0.5 indicate a longer deceleration phase. For peak speed, we encountered significant main effects for action and a significant interaction of action by object, with significant differences for the glass, plate, and wine glass objects. This indicates that, for example, persons were more careful during the placing movement of these objects. For the proportion of time to peak speed, we encountered significant main effects for object. Post-hoc pairwise comparisons reveal significant differences between the following object pairs: cup cutlery, cup plate, and cup wine glass. On the object level, all the PTPS values were significantly lower than 0.5. This means that both reach to grasp and reach to place movements had a longer deceleration phase. We observed action-object dependencies in the PS and the PTPS parameters of the speed profiles. In particular, differences on the object level indicate that intrinsic object properties modulated the motor behavior in VR. Our results show that unconstrained actions in VR show characteristics which are also typical of actions executed in physical environments. Reach-to-grasp movements are faster than reach-to-place movements for some objects. And reach-to-grasp and reach-to-place movements are asymmetric with longer deceleration phases. Furthermore, the object-dependent differences suggest that cognitive factors modulate motor output based on object type and the action. Our results are suitable when applied in the design of object manipulation rules. For example, measuring high speed combined with a short deceleration time could trigger the breaking of a glass. This would encourage a more careful behavior during subsequent manipulations. Our results can also be applied for the simulation of object manipulations performed by virtual agents. This would enable to produce a more human-like behavior, and it would also improve the object weight consistency for object manipulations. Thanks for your attention.